Imagine a space where invisible lines of force dictate the motion of charged objects. This is the realm of the electric field, a fundamental concept in physics. An electric field is a region around a charged object where its electrical influence can be felt. It's like an invisible aura that exerts a force on other charged objects. The strength of the electric field is determined by the magnitude of the charge producing it and the distance from the charge. A stronger charge creates a more intense field, just like a brighter light illuminates a larger area. Similarly, the field weakens as we move further away from the charge, analogous to the dimming of light with distance. Understanding electric fields is crucial for comprehending how electricity works. They are the invisible bridges through which charged particles interact and influence each other. From the smallest atoms to the vast expanse of space, electric fields play a ubiquitous role. Electric fields are generated by electric charges. These charges can be positive or negative, with like charges repelling and opposite charges attracting. Think of a battery, with its positive and negative terminals. Each terminal possesses a different type of charge, creating an electric field between them. The electric field lines, often depicted as arrows, provide a visual representation of the field. These lines emanate from positive charges and terminate on negative charges, indicating the direction of the force that a positive test charge would experience. The density of the field lines represents the strength of the field. More lines packed closer together indicate a stronger field, while fewer lines spaced further apart represent a weaker field. Imagine moving a small positive test charge within an electric field. Work must be done to move this charge against the force exerted by the field. This work done is stored as potential energy, known as electric potential. Electric potential, often referred to as voltage, is the electric potential energy per unit charge at a point in an electric field. It represents the potential for a charged object to do work when it moves from one point to another within the field. The difference in electric potential between 2 points is called potential difference or voltage. This potential difference drives the flow of charge, much like water flows from a higher elevation to a lower one. The electric field, E, at a point in space due to a point charge Q, is given by Coulomb's law, E equals kq over r squared, where k is Coulomb's constant, and r is the distance from the charge. This equation tells us that the strength of the electric field is directly proportional to the magnitude of the charge, and inversely proportional to the square of the distance from the charge. The electric potential difference V between 2 points in an electric field is given by V equals ED, where E is the electric field strength and D is the distance between the 2 points. This equation highlights the direct relationship between electric potential difference and the strength of the electric field. These equations, and others like them, provide us with powerful tools to quantify electric interactions. They allow us to predict the behavior of charged objects in electric fields and to design and optimize electrical devices.